Mr. Sams, you are wearing a baseball helmet.
I am, yeah. You know, last few times ago, I forgot to wear my safety glasses, and you gave me a pretty hard time about that. So I thought I'd come prepared today. A little extra safety gear. You never know what's going to happen in a chem lab.
Your eyes aren't protected. I could still like shoot acid into your eyeballs.
Oh.
Something like that.
So I need goggles underneath my helmet.
Yeah.
Well, we're not really in a chemical oriented unit, more of a physical oriented unit. So I thought I'd probably be okay.
Okay. All right.
So we'll see who comes out all right here. I got the helmet on. You got the goggles.
Yeah, I think we should probably do that.
Okay.
All right, folks. Today we're going to talk about periodic trends.
Mm-hmm.
I love periodic trends because they happen periodically.
And they're trendy. Yeah.
I see. We have 3 things to talk about: atomic size, ionization energy, and electron affinity.
Yeah.
Woo! So let's get rocking on this. Okay, first of all, I want to talk about size.
Yeah.
Atomic size, what does that mean?
That's the size of an atom.
Yeah, that makes sense. The size of an atomic size, the size of an atom. It totally makes sense, doesn't it? All right, so what determines the size of an atom?
Usually how much stuff is in the atom.
Stuff. Now, what kind of stuff do you find in an atom?
Well, we've got protons.
Yeah, MOPs.
We've got neutrons.
Neutrons.
And we've got electrons.
Electrons. But you know, only one of those indicates size.
Yeah, it's the electrons. Because the protons and neutrons, they're really densely packed in the nucleus. So that, I mean, frankly, that's hardly any of the actual space that the atom is occupying. And
really, folks, it's the outermost electrons that determine the size, because they are the furthest from the nucleus. They are the edge of the sphere, if you will. Think about an atom as a sphere. So, but some atoms, now atoms are small.
They are very small.
Really small. How many atoms in an orange?
Lots.
Lots. The same thing. You have to blow the orange up to the size of the Earth, and then the atoms would then be
the size of an orange.
No, actually the size of cherries.
Cherries. Oh, wrong fruit.
Yeah, well, but close, yeah. Okay, but some atoms, now what we're talking about today is not the size of atoms, just how incredibly small they are, but we're actually going to compare the size of one atom to the size of another atom. You see, some atoms are tiny. They're all tiny, but some are uber tiny, and some are bigger than others. So what we're trying to do is figure out which atom is the biggest compared to the rest.
Yep.
Now, there's a trend that helps us to understand that. Okay, so let's take a look at this particular chart right here that helps us get a picture of which atoms are bigger.
Yeah, now the easy one is as you go down in a family, they get bigger.
So if you look going down here, we've got this mirrors the periodic table. Lithium and sodium and potassium, rubidium are all the first row elements, the alkali metals, and hydrogen, of course, too. And of course, as you went down, you went from 37, I think this is picometers, up to 265 picometers. And that's true in every column. So if you look at the family of nitrogen, he's 70, 110, 121, 141, 155. So that makes sense, doesn't it?
And they're getting bigger because as we go down, we're adding energy levels. As we add energy levels, the electrons get further away from the nucleus.
Another way to think of that, folks, is what you're essentially adding is you're adding another shell. All right, you have, I mean, we've learned electron configurations. You know, let's say from hydrogen, that's the 1s shell. And when you jump to lithium, this would be the 2s shell. All right, this would be 1s1 and 2s1. Do you get the idea? But we have a particular issue here. What's the thing that's kind of odd, Mr. Sams?
Well, as we go to the right, even though we're adding more electrons, they're getting smaller.
Yeah, I noticed that the hydrogen here is 37 and the helium is 32. And then in the second row here, lithium 152, 113, 88, 77, 70. And you can see they typically get smaller. A few exceptions here.
A little bit exception at the end.
But pretty much the general trend, it's not a hard and fast rule, is they get smaller. Now that's kind of an odd thing. Now, let me go back and tell you, my old high school chemistry teacher, she had a way to explain this. She called it the girdle theory. Yeah, what's a girdle?
I think it kind of squishes stuff. Like body parts.
Yeah, so females...
Makes you look skinnier than you really are.
Yeah, you get the idea. So let's say that you are a young lady who maybe likes chocolate.
Okay.
And you love chocolate. Chocolate. In fact, it's about Valentine's Day, and isn't there like all this chocolate stuff going on? So you eat chocolate, and so what happens, of course, as you eat chocolate?
Well, if you eat too much chocolate, you get a little on the larger side.
Well, actually, in this case, you're going to get more massive.
Okay.
And as you get more massive, your girdle will squish you in a little tighter because you can cinch it better. Yeah. So as you get more and more massive. Because actually, one other point here as you go across the periodic table here, the elements are getting heavier.
Yeah, we're adding protons because the atomic number is going up.
So, for example, lithium has an atomic mass of 7, and beryllium is, I think it's 9, isn't it right? I think it's 9 or maybe 10, whatever. Let's say it's 10 or whatever. So it gets heavier, where neon, I believe, has an atomic mass of 20.
21,
maybe
yeah.
20 or 21. And so you go from 7 to 20. So think of a 7-pound girl. That's really light or whatever, but you get the idea. And she gets heavier and heavier and heavier. She gets to 20 pounds. But she gets smaller and smaller because her girdle gets tighter and tighter and tighter. But then one day, she just reaches that point where the girdle can't hold it anymore.
You got to go from a size 4 to a size 5.
She's got to get the bigger girdle.
Yep.
Yeah, and so she goes from a size, let's call this size 1 girdle, size 2 girdle, size 3 girdle. She jumps to a size 3 girdle, and everything just kind of flows out. And then she becomes sodium. And then, of course, it gets tighter as she keeps eating chocolate. I don't know. Does it work for you?
Sure, it works for me.
Yeah. Now, the big question, what we actually want to answer, does that sound right? The big question we want to answer is, why does this occur?
Yeah.
Okay.
By the way, if you're ever asked to explain these on like the AP test, do not talk about girdles and chocolate, okay? Talk about what happens in terms of protons and electrons, which is what we're going to explain to you now.
So this is the real explanation and not the Bergmanian girdle theory. Okay. So this is the real one. Listen very carefully.
Yes.
All right. So what's going on as you're going down, and I think we've already explained this, as you're going down on the periodic table, what happens is you're adding energy sublevels, or shells, or orbitals.
So the more shells, the bigger you are.
More shells, you get bigger.
That one's easy.
So the hard one to explain is what happens as you go to the right. So let's go to a new screen and look at this. So as you are going from, let's go from the sodium family.
Okay.
So let's take the element sodium with his 11 protons and 11 electrons, and he has a particular size.
Right.
Okay. Now, actually, let's draw it this way. The 11 protons are in the center, and then you've got 11 protons on the outside. Electrons, pardon me, on the outside. And then the next element after that is magnesium, and we know magnesium is a little smaller, not a whole lot smaller. He has 12 protons and 12 electrons in the outer shell. Now, why does it get smaller when we sort of go from here to here?
Well, in the outer shell, they're both in the 3s sublevel in that outer shell. So those electrons are just as likely to be anywhere in that 3s as the other electrons in that shell. So the sodium electrons and the magnesium electrons, they're in the same space where they could be. But magnesium has one more proton in the nucleus. As a result, it's going to attract the electrons closer to itself.
That's the key thing, folks, to understand, is adding one more proton. Basically, think of it like a magnet. You guys played with magnets when you were kids, probably, or just even in science classes. And when is a magnet strongest?
When it's closest to the thing you're attracting it to.
Right. So if I've got, I put the opposite sides of a magnet, this is more attracted than, say, this. If I had the same two magnets. But what I've done is I've essentially made the magnet in the center stronger. It's now have a 12 strength versus 11 strength. And so he can hold on to the same electron cloud, the 3s cloud of electrons, with an additional strength, which causes it to shrink.
Yep, pull it in closer.
And then when you go to the next element, which would be smaller yet, you'd have 13 protons and 13 electrons.
Boron. Aluminum, sorry.
It's aluminum, yeah. And again, I've increased the strength of the center piece of the magnet by one level, for one proton, which shrinks it a little bit more, and then you get smaller and smaller and smaller as you go across that particular row. And that's really why it's going. You're increasing, big fancy word, you're increasing the nuclear charge, the charge of the protons, by adding an additional proton.
Yep.
Make sense?
Yeah, there it is.
Okay. Second topic we're going to talk today is we're going to talk about something called ionization energy. Now, what is ionization energy?
That's the energy required to remove an electron from the outermost energy level.
To remove one electron from an atom. Now, I think, Mr. Sams, that
technically in its gaseous state too.
Yeah, that's true. In the gaseous state. Yeah, that's actually important in a little bit later podcast.
Yeah.
Okay, so it's in its gaseous state, and so I think we should show them a little bit more graphically.
Okay.
What ionization energy is. What do you think?
Sure.
All right.
Okay, now I have a feeling this is where my helmet might help me today.
Sams, why are you wearing that helmet? I think to wear the safety glasses.
I need safety
Folks,
glasses.
don't you think he needs to wear the safety
Probably
glasses?
safety glasses plus helmet.
I think he needs a safety glasses.
All right.
You're very tall.
Thank you. I do my best.
I'm short. Okay. Why are you holding tennis balls?
These
Mr.
are my
Sims?
electrons.
Oh yeah, electrons. So you're like an atom.
I am.
Oh cool. And I have a baseball bat.
See, that's why I'm wearing my helmet. I saw that when I walked in, so I figured I better put something protective on. I'm a little nervous. All right.
So what are you going to do now?
Well, I've got 3 electrons here, and I'm just going to kind of spin around.
Okay, so you're going to spin around. Maybe you should spin around further back behind here. So
further back here? Here, I'll spin around back here.
Okay, so I get to hit you, right?
You do. And when you hit me,
what's going to happen?
you're going to put some energy in, and I don't know. Let's see what happens.
All right, let's see what happens. So people, I'm going to hit them.
Ooh, I lost an electron.
Ah!
Well, see now.
Oh, what was that? That's like ionization energy.
That's right. You put energy in, and I lost an electron. So that's the energy required to remove it. But now.
Oh, you're smaller.
I do, and well, I have 2 hands, and I had 3 electrons. So it's kind of hard to hold on to all 3 with
I
2
see
hands.
that. Yeah.
But now I've got 2 hands and 2 electrons.
And
so
you're like,
pull
you're
it a little
shrunk.
bit.
See, he shrunk, folks. He shrunk.
Yeah.
That's good because he's taller than me. Now he's shrunk. All right. So now I'm going to get to hit him again.
Yeah. Do it.
Should I hit him? Wah! Whack! Ah! Oh!
Lost another one. But now I've got my electron right here in my helmet. Yeah, nice and tight. Good luck getting that one out of there.
All right, I'm going to try it. Okay.
You're going to have to hit
now,
it
actually,
really...
what that illustrates is what's called the second ionization energy,
Right.
folks. When you remove the second electron. Now, I'm going to really hit him hard to remove the
Yeah, you got to get that third. You're going to have to hit me pretty good to get it out of here, I think.
Yeah, okay, all right. Ready?
I'm a little...
Set! All right, and now actually, folks, what he's done is he's shrunk big time. So in the first picture, he was big, okay? And then he shrunk a little bit. And then when I remove that next electron, he shrunk a lot of it. Okay, because we break into what we call what's the core electron. he's scared because I can take a bat, and I take a bat and I whack his head. All right, I think you get the idea.
Yeah, that was kind of scary. I'm going to leave this on.
I think you should.
I'm going to take...
So, hopefully that wasn't too freaky for you. So, to remove 1 electron, the second ionization energy is the energy to remove the second electron. So, it's the same definition.
And it's always higher than for the first. Always takes more energy.
The third electron is the third ionization energy. And there's such thing as the 4th and the 5th and the 6th and the 7th and whatever it takes to remove all of the electrons.
Yep.
Okay. Now, this particular table is the table of ionization energy trends on the periodic table. And so the highest substance with the highest ionization energy is helium. This is the first ionization energy. So if you look at this particular thing, let's think about it from the periodic table perspective. So let's think about that. So folks, I'm in front of the periodic table, of course, and so I'm talking about ionization energy trends. The substance with the highest ionization energy of all elements is the element helium, first ionization energy, okay? And so as you go across the periodic table, so if I take the third row here, sodium, aluminum, silicon, argon. Argon would have the highest ionization energy in a particular row. And if helium is the highest one, if I go back now, the substance with the lowest ionization energy, I'll have to get out of the way here, would actually be francium here, or francium, however you want to pronounce it. And so as you go down the periodic table, it gets lower and lower and lower. So the one that's easiest to remove is the francium. The one that's hardest to remove is the helium. Got the trend? All right. I'll get you later. All right, folks, back to the screen now. Basically, the key here is you can see the graph here. This particular graph illustrates what I just did in front of the periodic table. Hello. You get the idea. Is that helium, and then there's a big drop. Lithium is much lower. So the lowest elements on the periodic table, and actually it makes sense, is the alkali metals: lithium, sodium, potassium, and here's cesium. We don't have francium here, but cesium would be the lowest one that we have on the list. And that's actually because it's holding on to the electrons the weakest.
Yeah, and that's why they're also very reactive and explosive.
Yes. Now, another thing to talk about that we should get to. Actually, did we have the Y thing? Yeah, we'll do that there. Okay, sorry. Folks, this is a table of successive ionization energies. So the example that we did with the baseball bat and Mr. Sam's a bit ago is actually, I was using the example of magnesium, actually. And to hit him the first time, I had to apply 735 kilojoules per mole of energy. And that's where he lost the first electron, the first ionization energy, the first ball. The second ball was 1445, about double, actually, to remove the second one. So it took more energy to remove the second one, again, because it was smaller. And then the third ionization energy, I don't know if you noticed this, but this, what do you see there, Mr.
It's huge!
It jumped from 1,400 to 7,000.
Yeah.
And you see, that's because that third electron was embedded in his helmet. It was what we call a core electron. The core electron, and core electrons are held very strongly.
Yeah.
It's actually because they are in a inner shell.
Yeah, in terms of magnesium, magnesium's in the 3s. So it's got 2 electrons in that 3s. You remove those 2, everything else there is now in the 2p. So to get that third one out of the 2p, which is full, which is nice and stable, you're going to have to put in a lot of energy to get it out of there.
Let me illustrate it this way. In this particular picture right here, I have the 3s electron. I had to get rid of the first electron, that was the first hit. I got rid of the second electron, that was the second hit. To hit that third electron out, I now am trying to hit it out of the inner core electrons, and those are very difficult to break out because, again, they are a smaller atom. Okay, now speaking of smaller, all right, why does this happen? You know, in regular chemistry, you might have learned about this trend and just sort of memorized it, but you never understood the why. The
increases as you go up and to the right. That's about all you learn about it in regular
So you know the trend, but why is the trend that it is? So let's think this through as we do this. It has to always come back down to the issue of the size. Okay? Now, Mr. Sams, I think you have a way to help explain that.
I do. It's the babysitters and kids analogy. So let's go back to our magnesium atom that has 12 protons and 12 electrons. Okay, now this is our neutral magnesium atom. And notice we have 12 protons, 12 electrons. If the babysitters are the protons in the middle and the kids are the electrons running around the outside.
The babysitter is the protons.
Yep.
And the kids are the electrons.
Crazy electrons running around. Okay? So here we have a 1-to-1 ratio. We have 12 babysitters, we have 12 kids. So every babysitter has 1 kid to keep an eye on.
Okay, that'd be really good, actually.
Right. So, you know, it's going to be pretty hard to get one of those kids out of that situation because there's a 1-to-1
makes
ratio.
Sense.
There's eyeballs on every kid. So you put some energy in, you get 1 kid out of there. Okay? So now we've removed 1 electron.
So you got 12 protons because 1 kid, mom came, picked him up.
Mom came, gone away, or got distracted by a toy, whatever, is now gone. So the 1 kid's gone.
Oh, so actually you got kidnapped.
Yes, the kid got kidnapped, so some energy was put in and took the kid out. Now, at this stage, we now have 12 babysitters supervising 11 kids. There is now more babysitters than kids, meaning every kid is going to have at least 1 set of eyes on them, making it even more difficult for that kid to get kidnapped or be distracted and lured away by a toy.
Oh, I see.
Okay? And so you're going to put even more energy in to get another kid out of there. So let's say that happens, and now we're down to 10 kids. Okay, so now we got 10 kids and 12 babysitters. Now there's even more eyeballs on each individual kid because they're, and not to mention that, those electrons are pulled even closer in.
Yeah.
And so the kids are closer in proximity to the babysitters. There's more eyeballs on them. It's going to be even harder to get another kid.
I like the analogy. It works. Yeah, it works for me. Yeah. Now, folks, the key thing to understand, you can't, of course, on the AP test, talk about babysitters.
Don't talk about babysitters and kids.
It comes down to the issue of the size.
Yes.
Because as you take away an electron, the atom shrinks.
Yep.
Actually, now it's an ion. Yep. The substance shrinks, the ion shrinks, and then it becomes smaller, and therefore the protons in the middle have a greater attractive force because they're closer together. We talked about the closeness of, say, magnets. It's that concept, and it holds it more tightly. So you have the same nuclear charge, or the charge of the protons, but you have less electrons. That is the key thing to understand as you look at these trends. So why does there increase as the number of electrons are removed from the atom? Because it gets smaller. And then there's the same nuclear charge holding on to less electrons. Think of your babysitter analogy. All right. Now, why is there such a big jump in energies at certain portions on the table? Now, we talked about that just a minute ago on this table. And what was the key word here?
Core
electrons. You break into a core electron, and it's very, very difficult because that shell is much, much closer to the center of the atom, right? So this is the outer shell, and this right here is the inner shell. And of course, it's closer, and therefore much harder to break free. Okay. One last thing to talk about. It's called electron affinity. Electron affinity is what?
It's the energy that is released when it gets an electron.
When an electron is added, yes.
So these numbers are always shown as negative values because
Yeah.
it's exothermic. The energy is going out.
And the trend is not quite as strong. Basically, the ones that want electrons typically are your elements that are your halogens. So the halogens are the ones that are that. So for example, chlorine and fluorine, which want one electron so they can look like a noble gas, have high electron affinities.
Yes.
All right? So, okay, folks, that's and the trend basically, the trend is actually not very strong. So it's just kind of odd. You're still wearing your helmet. You got the goggles on.
I do. I got helmet and goggles. I'm super safe today.
You are safe
I actually
today.
kept them on through the whole
Of course, I was hitting you ahead with the bat.
With the bat. I know. I'm a little nervous now. I think I might scoot over here.
Maybe that would be good because I'm going to find my bat and get you!